Welcome back to the Fullerton College Pre-Press class. This is Professor Ben Kiewit with part 2 of not quite sure how many of the PIA's section 4.2 of the Pre-Press Training Manual, Color Reproduction. So we're talking about color separation. When you take the halftone dots, the information of each of the channels plus black, and you print them on top of each other, at a normal viewing distance, those dots will disappear. Due to something known to the art world as Gestalt imagery, humans see the whole as opposed to just the parts. For instance, if you see a house, a typical, stereotypical icon of a house that you think of, you look at that house and you don't see it as a rectangle with a triangle on top of it. You see it as a house shape, which is a rectangle with a triangle stuck to it. When a car drives down the street, you don't see 4 tires, some side paneling, windows, license plates, passengers inside, maybe a spare tire on the back, and the color of the paint as separate things. You see a car come by, and those are simply details of that car. The same type of logic also applies to how we see, one more thing, if you see a brick house, sorry, a little George Clinton coming through there, but if you see a brick house, you don't see all these bricks. You see a house that happens to be made out of bricks. Humans look at the whole picture, not as little details, not originally. You can then focus on the details later. We first try to get an overall impression, which is how halftone printing is functional. We see the image, even though it's composed of billions of little tiny dots all there on the page next to each other, and there's no mixed ink. To us, we first try to make sense of the whole thing before we look at the details of how it is. So we see overall, if a certain amount of light is removed from that white light that reflects off the paper, even if it's not solid, we still see an area. For instance, that red barn. Let's talk about the red barn bridge again. The red barn bridge has yellow and magenta dots on it. And that's it, basically, just yellow and magenta, maybe a few other bits if you zoom in far enough. But you don't see those 2 dots overall. You see, or individually, to your eyes, you know that that region that makes up that red color has mostly the green and mostly the blue light removed from it by its magenta and yellow ink, respectively. So you just see an area that is reflecting red light overall, even though some parts are magenta and some parts are yellow. If you're far enough away, your eye just sees the area as the sum of its parts. You see the total. As long as the dots are small enough and as long as the dots are close enough together, you don't see the difference. And that's how it works. So screen angles. It's important that these dots get lined up the right way. There's an animation that if Flash was still supported would play right here. I'll find another way of showing you one of these in a separate video on this same lecture Canvas shell. Anyways, halftone dots, for the most part, are printed in neat rows. It's kind of like watching a marching band go by. Remember marching bands? Yeah, good times. Think about a marching band in a parade. I'm not talking about cool. I outed myself as a nerd again. I said cool before I said field show. Yeah, I did totally play trombone. Anyways, in a marching band, you look at the band and you see all the people marching in their rows down the parade, all playing whatever song they're playing. Something cool, something fun, hopefully Holst. I like Holst. But anyways, everyone in that band is marching in the rows regardless of how big or small they are or big or small their instrument is. So the same grid of people walking down the street playing that music is in place, whether they're band jokes and stereotypes coming here, whether they're the 30-pound flute player who has to be tied down in high wind situations, or whether they're the large guy playing the sousaphone or the bass drum in the back of the band. Either way, they march in the same rows. So if you look at one of those bands from above, which you get to do once a year on New Year's Day from the sky cameras over Pasadena, you can see that they're in the same rows, but in some rows the people are bigger, and some rows the people are smaller. And regardless of the size of the instrument player, they're in the same rows. This is called AM screening, or amplitude modulation, for those of you who are older radio buffs. And this means that no matter what, our halftone dots are printed in that same grid, just like the band. The grid doesn't change. It's a square grid. But the size of the dots does. The bigger the dot, the darker the color. The smaller the dot, the lighter the color. Now, to avoid problems, we print them at different angles. If they were all the same angle, you'd get either big chunky dots with lots of white space, or you'd also get something called a moire pattern, an interference pattern, which is something that every kid knows. If you're riding in a car, or even riding on a bike fast enough, or sometimes walking past two chain link fences, you kind of see those weird dancing zebra zigzag shapes between the fences as they overlap as you walk, drive, or ride by them. That is a moire pattern. And that also, anytime you have two different patterns of images, two patterns of grid online on top of each other, you're going to get them. It's impossible not to get an interference pattern. So what did we do in printing? We found one that people didn't mind so bad. So if we set up the yellow at 90 or 0 degrees, that's the same thing if you're talking squares. Yellow's light, so you're not going to notice it as much. It can be a normal square grid, and it's not going to throw people off too much. Magenta's tilted to 15 degrees, cyan at 75, black at 45. When you put all those together, yeah, I really wish I could show it to you right here, you get something called a rosette. You get larger little spots, little circles, where all the dots line up to make little rings. And these dots basically make bigger dots. And we've discovered that that is the least disruptive shape to the human vision experience. Oh, Mr. Vacuum. Hold on a second. Sorry, that was my robot vacuum. Who's in no way called Mr. Suckpuck? That name was rejected by the household. Anyways, back to this. You have those different angles, they line up. We've discovered that larger circles and larger dots don't break the experience the same way that other interference patterns, well, interfere. So color reproduction. Remember, we are not color matching. If you want color matching, you can use the Pantone matching system, wherein you use individual inks of the color that your client wants. That is different than doing a CMYK process build, because you're making a close facsimile. You're not going to get exact. You're going to get close. You cannot match on press because there's something called tone and gamut compression. You're only able to produce so many variations of dot size on a printer. And the variations in dot size, the level of control you have over the size of your dots is the level of control you have over the interpolated in between colors. We'll talk about this more later, I swear. But anyways, in excruciating detail, we get to the chapter on output and how computer pixels turn into machine pixels, turn into halftone dots through laser spots. We will get there. How exactly is that math done? Don't panic. You don't have to do the math. Anyways, so we're trying to produce a color as close as we can using what we have without getting exact. If you get exact, bravo, good job. Happy for that. And again, repeatability and consistency are the keys to printing, more than accuracy. I can tell you from experience, one of the worst things that can happen to you in printing is to print something by accident and get it right. Because when your client wants that done another time and you're not quite sure how or why it happened, good luck doing that a second time. That builds these expectations that you can never meet again. It's better to do something you're able to do many, many, many times than to do it perfectly once. So, requirements for reproduction. Here's the things you need to get: tone reproduction, gray balance, and color correction. Let's go. So, tone reproduction is talking about contrast, brightness, the white to dark level of printing. Remember that a printing press is binary. Cue Binary Sunset, one of my favorite songs. Thank you, John Williams, for defining my childhood. Anyways, binary means two things. In computing, it's 1 or 0, on or off. And that is actually how printing has always worked, even before computers. Any printing image carrier only answers the question, is there ink here? So you can't answer that question with maybe, sometimes. That doesn't work. And a printing machine either puts ink down or it does not. It does not water down the ink like a watercolor paint and paint a glaze on top of less ink. You can't do that yet. Maybe someday, who knows? But as of now, all printing either drops ink or does not. So we have to use the different size dots. The white space between the dots are what gives us the illusion of shades of gray. Remember, if you're back far enough from it or the dots are small enough, your eye can't see the difference between the dots and just the overall area that they define. So here's some tone reproduction differences. You see the original photo in the center, and you can see where they add highlights, which means the lighter parts are brighter. More shadow means the darker parts are darker, minus highlight and minus midtone, where there's less highlight color and there's less midtone color, where the different parts of the image are brighter or darker. You're playing with contrast. Up next, we have requirement number 2. Number 2 here has actually become an entire color management method. For those familiar with it or at least heard the name, G7 color management by Idea Alliance, or co-opted by Idea Alliance by Don Hutcherson, who I've met, name drop. This system works on matching gray balance to control your entire press's ink mixing. I'm saying mixing with an asterisk because obviously we're not actually mixing. But anyways, you can control all the colors by landing the gray correct. So gray balance means you are using cyan, magenta, and yellow mixed together to make a neutral gray. If it's correct, it should be neutral. I love this picture. Let me zoom in a little bit on it here for you. Looking at close, obviously it's made up on a computer screen, but still, you should be able to see 2 grays that look very nearly identical. One should be made using only black ink, and the other should be made using cyan, magenta, and yellow, but no black ink. Excuse me, computer. Thank you. There we go. So, leaning back on our color theory a bit here, we know that in subtractive color, equal parts of cyan, magenta, and yellow should equal black, because they're all removing red, green, and blue light. And if you remove all the light, you get black, correct? Yes, in theory. In practice, remember how we had to add that 4th plate of color? We had to have the black ink to be able to reach those dark colors. It falls short. There's chromatic entropy out there where, yes, in theory, this should happen, but we've found none. We have found no pigments on Earth and been able to make no pigments pure enough to actually do that. In fact, if you look at the numbers here, you might also notice that it's 50% black on the left. K means black for some reason. There's a lot of debate on this. I don't have a solid answer. Some people think it's because they didn't want it to be B because they don't want it to be blue and get confused with cyan. Some people think that K stands for key. Yeah, ask any printer, you'll get a different answer on that one. But K does mean equal black. They all agree on that one. We all agree. K equals black. We're just not quite sure why. It's one of those age-old tales of the sea. Everyone has their own version of it. But anyways, so 50% black, but on the other side, it's 50 cyan, but only 40 magenta and 40 yellow. This is a holdover. This is a legacy value because early color printing, the cyan inks weren't bright enough. So you had to make the cyan darker because the magenta and yellow would easily overpower it. Even in G7, they've kind of kept these legacy values around because printers got used to it. And it's easier to work with what you know. But anyways, if you're doing black and white work, you don't need this. You're just using one color of ink and you just have to deal with how does it look bright, how does it look mid, how does it look dark, end of story. But for gray balance, you want to make sure that that mixture of cyan, magenta, and yellow actually makes a neutral gray. Here's what happens if you don't. A balanced gray means that all the colors in the image will come out looking neutral. This is one of those things, one of those horrible things about pre-press. You do your job right and nobody notices. You do it just a little bit wrong and everybody's on your case. There's a phrase from a movie that I don't quite like, but I like the phrase from, I believe, Pushing Tin from back in the days, which is not a great movie. I don't appreciate anything that's about cheating in relationships. But anyways, you know, you land, the movie's about air traffic controllers. And the phrase is, you know, you land thousands of planes safely every day, but you have one little bit of air collision and suddenly everybody's up in arms. Well, yeah, one little mistake. You do it right, nobody notices. You do it wrong, everybody notices. So if you're totally neutral, your gray balance is totally correct, it'll look just fine and you won't notice it. If it's a little bit wrong, you can see it can look a little bit cyan, it can show up a little bit bluish. It can look a little bit yellow, that's a common problem. Also because paper tends to be on the yellow side, so it leans that way even more. Magenta, I know of some printers, I'm not gonna libel them, who do this, whose presses constantly print too heavy on the magenta. And in fact, I built my own color correction curve back when I was in industry when I worked with them because I needed stuff to look neutral and I knew they were gonna print way too much magenta. And sometimes too much cyan and magenta, also not very common. More often than not, it's going to be a little bit too yellow or too magenta. And that comes from the gray balance not being gray enough. All right, we'll come back for one more, hopefully just one more video, which should finish this out.